point that I need to give lectures and.
So if we remove the waiting point, we just. It's not important to let people in because they already in our meeting.
Yes, but please come in time, okay? I will make another screenshot later, but I ask all of you come in time because it's convenient for me and for you to continue lecture without interruption. Of course, I understand there can be some problem with internet, so, but if it's possible, please. Okay, so and this is also the simulation. The previous one, this one, it's a body simulation with a billion of particles, and you can see the number here, and they can take count hydrodynamics, dark matter, everything which we can, they can take count. Here you can download even the movie, but what I would like to show you, because we will speak today about cosmological principle, you can see, so we believe that the structure of the universe, of course, the structure which is larger than 100 megaparsec. So it's we will write later this cosmological formulation of cosmological principle. So this is like this. It looks like a spider net with many voids, so empty space. Empty space and filaments which connect the huge clusters of galaxies. Also, what else I would like to show you? You can write in Google Universe in the Box. It's one of the talk which was in Krakow symposium just July, and where you can find also some interesting issues which are related with the simulation. And by the way, you can find even here the book simulation, this one, and simulation and the quest to code the cosmos. For example, I can jump here. This is, as you can see, this is a site of European Space Agency, and it was really a huge effort that July this year was launched the satellite, the telescope Euclid, and we are waiting, of course, for the results because it's a long time to reach the Lagrangian point, the place from which this telescope will work, and to taste everything. So, but just to feel what is this, you can also to look on this. So this
in the past 20 years, cosmology has undergone a transition towards precision science. The standard cosmological model has been established, and its parameters are being measured with accuracy. Euclid will improve this model's precision and help us unveil the dark universe by studying the large-scale distribution of galaxies and cosmic structures. At 1.5 million kilometers from Earth, we witness the stars in the Milky Way, our galaxy, observed by Gaia.
So
Euclid will impose
now you
highly
can see
stringent
how he
constraints
scans
on the cosmological model that governs our universe. Euclid will generate images in the visible and infrared, covering 1/3 of the sky. We have created the largest and most comprehensive virtual galaxy catalog.
So this is a point that with Euclid we will obtain a lot of data which allow us to
We're going to fly through our simulated universe.
this
is the
to
simulated
convince
dark matter
observations
distribution. We note
with,
it is not randomly
simulations.
distributed, but
now you can see
it rather forms clusters,
in principle on this
filaments,
video
and
as I
voids in
explained.
between. Galaxies are traces of the dark matter distribution. In this visualization, they are shown with fake colors depending on some of their properties. Note
Okay, I will stop here so you can look this by yourself. I will not spend time. What is important that that you will after my lectures you will understand this too. For example, the scale when it's explanation how far from the present time we can look inside of the universe and inside of the time in principle. So you can see, for example, the scale below, and this letters CMB, dark ages, development of galaxies, and so on. And now, first stars and galaxies like this. So this is just to feel that cosmology is really field of research with a high technology. Not only space technology, but also computer coding technology, and we're using the top of the technological things which are related also with the machine learning and so on. About your ask, which are related with to this books, in principle, if you will write in Google cosmology book, you can see a lot. By the law of I don't know, Ukraine now, I can't recommend you books in Russian language. Unfortunately, we almost don't have books about cosmology in Ukrainian language. So there is a book Alexandrov in Ukrainian language, but it's you can find it in the site of Institute of Astronomy. But my lectures is not coincide with this book, and it's so if you write Alexandrov Institute of Astronomy, in principle you can find it in maybe in our library. What I can recommend from this huge number of the books, of course, it's I can see it. Cosmology, Steven Weinberg. So Steven Weinberg is a cosmologist, Nobel Prize laureate, and this book is really a translation in Russian, by the way. So not in Ukrainian language, and it's really nice book. There is an older version, not older version, but there is another book of Steven Weinberg, Gravitation and Cosmology, where you also, it's also very nice book, older, Gravitation, right like this. Yes, this is one. So, no, this one, Weinberg. In principle, so you can see here, Weinberg, Gravitation and Cosmology. In principle, you can find it in internet. So why is this older? It's a good in sense of representation of general relativity with which we will work with you. Also, of course, when we'll work with the general relativity, I recommend the book of Landau Lifshitz and the volume of the volume theory of the field. So also I would like recommend book. Okay, I hope you are right in your because I will change here search in the Google, but for me it's more simple to show you the book. Okay. Okay. This book very popular here, not only here, but in the world. There. So keywords, let's try. Yes, this one. So this book, Peter Schneider, Extragalactic Astronomy and Cosmology. It's a very nice book where you can find, but you know, such a very good organized, where you can find a lot of things, like you know, like an encyclopedia, but much more deeply. The theory, modern observations, some. So, and I recommend to read it, to look in this. You can find there theoretical astrophysics, observational astrophysics, cosmology, and so on. Okay, some of the part, for example, so if we are already in Springer, I can show you also okay. Okay, let me. Somebody wrote me, let me go in, but nobody in the waiting room. Okay, so so this is my book with my colleague Professor Capaccioli, which called Foundation of Celestial Mechanics. This is not exactly about cosmology, but you can find there the chapter with in-body simulation, with in-body problem, which using for simulations also the classical formulation of this problem. Also, there you can find the relativistic case of two-body problem, which are related with motion of the particle, test particle in the gravitational field of, say, black hole on Schwarzschild metric. So, in principle, can be useful. As you can see, is it to buy it? It's expensive. Hardcover book, almost 100 euros. But so, in principle, everything you can find if you want. Okay, I don't have a permission to distribute book because unfortunately there is some rules of publishing house. Okay, let's see, nobody yet. Now we can start. Do you have some question in this part which I showed you? No, any question? Just, I need to feel feedback from you to be sure that you are present. Okay. So if you have any questions, you can ask freely. Okay, no questions.
No questions.
Okay. Also there's a very nice book, deep book about cosmology, Gorbanov, Rubakov, with a really very good book, but it's in Russian. So, but you can find internet if you like. Also, of course, more popular, you can find the popular books. Hawking, Weinberg, the first 3 minutes, it's old book, but it's actual in principle. Okay, let's start with the science. So on this lecture, let's call this lecture observational properties of universe. So, as usual, in science, in physics, if we want to construct, to build some model, we need to use observations and experiments. So this point came to us from Aristotle philosophy. It's continue like this, and we need to overlook, to understand what we see, and after this to try to model it. And model allow us to predict something and to find the physical laws as a result. For example, to discover the law of gravity, we needed to observe the motion of the planets. And after this, slowly, I will not, this story, slowly the humanity came in the idea that planets move around sun, and finally discovered by Newton the law of gravity. So this is a point. When we want to model something, of course, the world is much more complicated than we sometimes can imagine. And the main point, what we start to work, this is to try to simplify the world around, or object which we would like to simulate, to try to simplify, because from more simple model we can go from this direction, much more complicated model, to come near to reality. This is the point. In our consideration, object is a universe as a whole. And and we understand that the universe is a complicated object, because there are many different kind of object, and of course we can't take into account everything. So we will try to simplify, of course, as usual we are doing. For example, instead to consider planets, which are very not a simple object, this is not a solid sphere completely, so it's a episode of rotation, and there are mountains like this. So, but we can consider it like a point mass sometimes, and sometimes it's enough. The same we will do here. But in any case, so we will speak about and we will try to reach and understand the universe, the model of the universe, which we call now lambda CDM model. We will not immediately to start to work with this. We will only to start to formulate the main principle which we will use to build this model. But just to that you will feel which is final goal which we would like to reach. So what it means, lambda CDM. This part we can write, so this is the first letters of the words, means cold, dark matter. And this lambda, it means lambda constant, which mean, and cold, sometimes I use dark energy. All this construction, when you will meet, so lambda CDM model of the universe, and everybody who are working in this field understand what it means. So it's like a code for us, but to understand with which things we agree. So it means that for present paradigm, that the universe consists of dark matter, and in principle, dark matter, if we consider the full budget of the universe as 100%, dark matter, it's around 27%. For example, we speak and we will speak about energy density. So, because we will work with general relativity, and instead to tell matter density, we will speak about energy density. So later, everything will be, step by step, we will feel it and we will see it in mathematics and physics, how it's appears. 27%. Lambda constant, and this dark matter, this is invisible. In any wavelength band. So no, if we will, for example, right here, which the diapason of electromagnetic waves. So this is radio, infrared, optic, ultraviolet, X-ray, gamma. Okay, if we put it in frequency. So gamma emission, this is very hard photons. And it means that we don't see that universe consists of such a kind of matter which we can't see in any part of the electromagnetic emission. But again, as I said in the previous lectures, we can feel it. We can feel it due to dynamics in gravitational system and galaxies, due to gravitational lensing effects, due to anisotropy in relict emission, which appeared on the early stage of the universe, so and so on. So we can't explain observational data without such a kind of strange things as a dark matter. Why cold? You can see here I put word cold. It means that this is not relativistic particles, but this is massive particles, and it should be particles. So this is the point, CDM. Lambda constant was used by Einstein in his equations, and we will see how this lambda constant appeared, and we will look on the Einstein model of the universe, and we will understand why he needed to involve this lambda constant. So this is such a I might say, how call it, substantial. This is lambda constant. It's understandable as something mathematical, okay, because it's a constant, lambda constant, and what? In principle, it's have a physical point about which we will speak, but we will also see that this lambda constant is responsible for something, for some substantial in the universe, which we call dark energy, and which is responsible for the expansion of the universe with acceleration. That's right here. Expansion with, and this is important, with acceleration. This is very important. Acceleration. So in total budget of the universe, this is for last observations. It should be 68.1. This is amazing, you know, when we speak about cosmological parameters with such a kind of precision, it's really amazing. And I must say that this new telescope, space telescope, which will start to work soon, if CLIT, will give us much more information and will make much more precise some numbers, and maybe, God knows, we will discover something new. And what about ordinary matter? So ordinary matter, we call it so, and it means lambda CDM model. It means that this is model of the, you can write lambda CDM model. This is a model of the universe, which consists of cold, in parentheses, non-relativistic dark matter and dark energy, which described by lambda constant. So for now, this words can be not understandable for you because come on, it's and what is this? But I hope and be sure, I may say like this, that in the end of the lectures, you will feel it and you will understand it. And what is important, you will understand the information which you can read, you can see in scientific paper and even on internet. I mean, even on internet in sense of popular things which show now, and I showed about Euclid. Okay, what about ordinary matter? Call it baryon matter. Usually it's a matter from which we consist of. So this is what we can see. This is matter which interact with electromagnetic interaction and which interact with electromagnetic emission and so on. This is only 4.9%. Of course, you can, in the first, you can ask about why you speak about baryon. So in principle, we can, when we tell about, say about baryon, we mean protons, neutrons. So this is an elementary particle which consists of quarks. And this particle which creates a nuclear. Of course, it doesn't mean that we don't want to hear anything about leptons, for example, electrons or tau leptons like this. But since the mass of the electrons much less than mass of baryons, proton and neutrons, usually we just don't care about leptons, and when we would like to calculate the budget, the part of the ordinary matter in the total budget of the universe, we just call it baryon matter. Okay? So the second point that it's really, we can see that ordinary matter, of which consists, you know, all what we can see, Earth, people, houses, sun, stars, galaxies, cluster of galaxies, all of this just a 5% approximately. And 95% something which we not understand finally, but we are sure that it is present in the universe. And this, as I already said before, and I will repeat it, this is fundamental not only for astrophysics or only for cosmology, but this is also fundamental things for physicists, for the physics in the whole. Okay, what is also interesting that from this, if we will consider this budget of baryon matter, it's approximately maybe 10% from this 5%, 10%. This is like you know, matter which is looks you know, represent in the stars. Stars, of course, stars, sky, galaxies, and galaxies. And approximately 90%. This is gas. So because when we consider the cluster of galaxies, so the group of the galaxies, they involve in hot gas environment. So, okay. So that you can see that this matter, which for us, which common for us, it's only, I mean, stars. Stars, it's only a small part of the budget of the universe. When we speak about, here we can speak about energy density. Okay, this is just a few words about universe and on which the universe consists of. And now I would like to do some attention in paradox, which we call Olber's paradox. I hope it's his name, Olber's, writing like this. Paradox. Very famous paradox. And the formulation of this paradox such a way that this is an equation which we can ask: why the night sky is dark? you can write why the night sky is dark. So why there is such a kind of questions, and this this question appeared Olbers start to ask about this, just ask about like 1926, before it was Thomas Digges who even in his name, last name like this. Yeah, it's 16, it's 1560, 76 like this. So it was the first question about this, because why? Because if we suggest that the universe is infinite, and the stars distributed homogeneous, and star, and
okay, I'm so sorry. We miss the last minute of your speech, because that's just was silence and any words which we can hear.
really?
Can you repeat your last yes, few last sentences?
Okay, universe decided to do something. Okay, thank you that you say about this. So Olbers paradox. Okay, did you hear the formulation of Olbers paradox?
Yes, why the night sky is dark, and also the thesis about homogeneity of stars distribution in the universe, and after that nothing.
So, and the point that if you will look, if you choose some point on the sky, and your line of sight sooner or later will meet the star, if the universe is infinite. And it means, and again, you change the direction, and again, your line of sight will meet sooner or later some star. And as a result, so I can, so here star, here, and we suggest that it's infinite. And here we have observer, okay? So we choose this direction, and sooner or later we will meet the star. We choose this direction, and sooner or later, yes, it also will meet the star. As a result, the sky should be very bright, even in the night. But we don't see it, so the sky is dark. It was one of the very smart question, why? So, and to find the explanation is the first to see that this is really like this, and it will be useful. Let call the letter N. It will be the mean, for example, mean concentration of stars in the universe. And let's call letter L is a mean stellar luminosity. Okay. The first we know that the flux, can write the expression for the flux depend on distance, as you know, and this is luminosity divided on 4 pi r square, where r is distance long. By the way, I would like to remind that luminosity, dimension of luminosity, this is energy divided on time. So this is power. If you want, it's erg in second. And luminosity, usually this is a physical property, physical feature of the object, of the star, for example. Yes, okay. If a star is a giant, it has such a kind of luminosity. If it's another star, so another luminosity. But we understand that if we will push and will move the star far from the observer, here put observer, the flux will decrease. The same as with a lamp. Move lamp and the emission and the flux from the lamp which are far from us is reduced due to the distance. So, but we want to, let's consider, I hope I will have place here. So let's consider some shell. Some shell with the stars. So, stars and universe, and we just choose some shell in the volume, spherical shell. So it's of course projection, and the radius of this shell r, and let's call this dr. Okay, this is the thickness of the shell. So, and I would like to find the intensity of emission from this shell, which created by this shell, shell of the stars. So this which point is a star. So I can write that the element, the intensity of the shell with the thickness of dr, this is di, equal L. Yes, and one point we also suggest that that luminosity of all object is the same, just to simplify. Of course, we understand that luminosity can be different, but let's consider it the same for all objects, for all stars. So it will 4 pi r square multiply on, and if you would like to find intensity, we need to multiply on concentration of the star. So this is flux, okay, this is flux, concentration of the star, and the volume. And in this volume, in this case, it will be the shell, so it will be r square dr. What is interesting is that as a result, we can see that we have only L divided 4 pi and dr. So you can write as a result, intermediate result, that the total intensity of emission of the stars, in this case, depends only on the thickness of the layer, this thickness, okay, of the layer. and don't depend on the distance from observer. So we don't have any dependence on R. It's only depend on dr. And okay, and now we want to obtain the total intensity of the star emission in universe. It means that what we need to do, we need to integrate from d and from 0. Yes, we 0, this is here. Observer, and to if the universe is infinite, so to infinity. So, and we can see that so ln 4 pi integral dr give us infinity. We very simply can see that really we should have a infinite intensity from all stars of the universe. And really the night sky should be very bright. So of course we put some suggestion in this very simple consideration, which is not so we understand that luminosity of the stars is not the same for all stars. That concentration and also can be also different, but it will not help us. In principle, can help us. But the much more important point, which allow to solve the problem with the night sky, this is a point that universe infinite in the space, but finite in the time. You can write in your conspect. Universe is infinite in the space, but finite in the time. So finite in the time. Why? Because there is a beginning. Because there is a beginning. And it means that the universe has an age. As a human being has age, you has age, and the universe also. And we need to put here to decide this to solve this problem. Instead of infinity, we need to put here c multiply on t, and how we call this time? T0. Okay, so if T0, this is the age of universe. And in this case, we really will not have infinity. So this is the solving of the Olber's paradox. The main, I may say. So others, of course, can influence, as I already said, but the main point is that universe is finite in the time. Okay, and we will see that when we will use a theory, we can see even without anything, we can see that really sooner or later we come in the point of the birth of the universe. But we will see this miracle later. Now, the next point, very important, that just a second. So the this is homogeneity and isotropy of universe. And mean distribution of the matter in the universe. Okay, when you say about universe, so what it means and why we can tell about this. This is this point is homogeneity and isotropy. This is observational fact. Observation of this come to us from observations. But of course you can tell that, but we don't see that universe is homogeneous, so the matter distributed such a way. But why I, in the beginning of the lecture, I showed you this simulation. Next time maybe I will show you the observation things because yeah, it's I showed on the simulation. But it was made several space survey, where you can see the distribution of galaxy, quasars, far galaxies, and they distributed such a way that the distribution is homogeneous in the scale more than 100 megaparsec. So 100 megaparsec, it means 100 multiplied on 10⁶ parsec, and just I will remind, and it means 10 parsec, and approximately, so 1 parsec, and this is 10 in 18, so it's like approximately 3 multiplied on 10 26 centimeter. So this is scale more than inside this, and this scale correspond to the scale more than the cluster of galaxies. For example, if you say about our, we call it home, I might say this is a home group of galaxy, our group of galaxies, including our Milky Way. So this is the scale of this group of galaxy, 3 megaparsec. Where, for example, we are gravitationally connected with Andromeda galaxy and others 40 galaxies in this group. So if we there is a super clusters, for example, as a Perseus, fish in Latin, I forget, pesce in Italian. So, and this is the scale of this supercluster already. Sorry, like 150 megaparsec. This scale is much more than the cluster of the galaxies. And if you will look, if you will remind this the structure, so I can jump quickly here. Maybe simply to show this one. So it means I can't use here my pen. So, but in the center where there is a scale 125 megaparsec, divide on h, this is later we will just some number, which almost equal unity, no 0.7. So you can see that really it looks like a homogeneous. And also, by the way, you can see that, but this is simulation. This is not observation. This is simulation using with the help of supercomputer. But also you can see that the distribution is isotropical. So, and this is the second point. Okay, And what principle means isotropy and homogeneous? So homogeneous, it means that we can have distribution like this. This is homogeneous, okay? So if I will take the scale like this, for me it will look like a homogeneous, so much bigger. Isotropical, it means that we have distribution like this. Oops. Okay. Oh, it's not beautiful circles, but you understand the idea. So it means that doesn't matter if it's here, and we will look in different directions. This direction, doesn't matter. You can choose any direction. So this is isotropy. This is homogeneity, this is isotropy. And this is very important point, because from there is of course equation, but okay. And the first we can formulate it called cosmological principle. After this we can speak a little bit about this. So cosmological principle. The formulation of this principle means that our location in the universe is not remarkable. Second, is not special. Okay, we can tell like this. So our location is in the universe is not special. So if we remind Ptolemy's system of the world, of the universe, the Earth had a special place. So everything was around Earth. Later, it was the sun, and planets move around sun. So it was a revolution, Copernican revolution. But in any case, it was equation. Sun is the only existence in the universe. So it was a different kind of object, and how they distribute. Now we can tell. And it was, sometimes ago, it was very pity, because when the Earth was in the center of the universe, it was much more gentle, because, we were all time under care of the God. So he looked on from the point of the people in this time. He falling for us, he's care about us, so we can pray and ask for something. When later the sun became in the center, it's but in any case, now unfortunately we can see that really our position is not remarkable, is not essential. So we are just one of the point of this infinite world. It's maybe sad to say about this, but this is what we have. And this is maybe stronger formulation of the cosmological principle. More mathematical, more physical formulation. Also, please write this formulation, because I will ask exam and we will use it. The universe is homogeneous and isotropical on the scale more than 100 megaparsec. So also this principle has a name, Copernican principle. Через C Copernican, through C Copernican, okay, Copernican principle. You already understand why, because Copernic shift Earth, I might say in parentheses, of course, from the center of the world, and now we shift everything, including the sun. So the formulation of Copernican principle that universe doesn't have special observers. Doesn't have special observers. So the person who observes the world. And the global characteristic of the universe in each fixed moment of time, are the same in all points of space. Are the same in all points of space. It's understandable.
Sorry, can you repeat all this?
Universe doesn't have some special observers. And the global characteristics of universe in fixed moment of time are the same in all points of space. So, because it means that, and if we discovered something here, some global, I say about global futures, global characteristic of the universe here, it will also work here. The same will be here or here. I don't say about, if one part of the universe, the star will appear. It doesn't mean that in each point it will appear. We say about global characteristic of the universe. It means the behavior of space. And because we will work with general relativity, and we will see that the expansion of the universe is related to the expansion of the space. We can tell about global distribution of the matter, with scales like this, and the time evolution of the universe. Of course, there is a question, why the universe like this, homogeneous and isotropical? Why, what's happened that the universe became like this? And this is right question. And we will find the answer on this question later. So we have 4 minutes. Okay. So in this case, this 4 minutes I will want to use for the next point which we observe. This is pauses before. Okay, this is cosmic microwave background. So this I would like to put inside this homogeneity isotropic cosmology comprehensive. Okay. Which call CMB. So you can hear this this abbreviature CMB. So this is cosmic microwave background. This is emission, which kept from the earliest stage of the universe. So this radiation which came to us, which it's better to say, which was fixed don't change essentially, starting from the time when the age of the universe was 3,000 years. T0 I use for the present time, so okay, TCMB. And we will look on this more precise, and we will speak about this later. But just to say that this cosmic microwave background appeared at the end of the hot stage of the universe. So in principle, when as we say, the radiation decouple finished to interact with the matter. And why it's important? So this cosmic microwave background, we can feel it. It's approximately the number, the density of this background. It's like 400 photons in centimeter square cube. So it means that everywhere there's photons, and what is important that this background show us that the distribution of this emission is also homogeneous and isotropical in the first level. And it tells us that the universe was like this even when it was very young, 300,000 years from the beginning, from the Big Bang, as people like to use, from the beginning of the everything. So this is the point. Okay, it's time already. So, and if you have a question, please ask me, and we will continue. We need to continue more quickly. Today we spent time for some pictures, but we will go more faster, I hope, in the next lectures. Do you have some questions?
I have.
No question. I need to make a okay, screenshot. Yes, maybe I will make a screenshot at the end of the lecture. It's more wise. Okay, let's do it. Okay, thank you, and see you. So in the next lecture, we will finalize observational properties of the universe, and we will start to consider Newtonian case, and after this, we will go to general relativity. So if you don't have any questions, we will continue on Monday.